How did the GitHub stuff work for everybody? Okay. I know it's going to be a little bit weird with Eclipse. If we were going to spend significantly more time in Eclipse, I would probably go through some of the plugin stuff to get it working more smoothly within Eclipse. But pretty quickly, we're going to be transitioning over to Android Studio. And Android Studio has a very good GitHub integration in it. So we'll kind of relearn it in 5 minutes using that now that you understand the kind of what's happening behind the scenes. Theirs, you won't have to do copying and stuff like that. You will literally just check it out. It's much nicer. And I'm sure Eclipse has something very similar. I just haven't used it. So rather than blow half a class time or something like that, figuring out a plugin that we're going to use for 2 weeks, let's cruise now. We'll just do the kind of ghetto version of GitHub for now. And then, well, it's actually the traditional version of Git is what we're doing right now. Then we'll enjoy the nice automation in Android Studio when we bridge over to that. Okay, so I want to start talking about something from the book talked about array lists, right?
Yeah.
Okay, so let's did it talk about generics, the little angle brackets with the array lists? Yeah, the type thing. Okay, yeah. So let's kind of talk about that for a few minutes as we transition towards something. And then we're actually going to do something related to how many of you were at chapel the day that Pastor Smith talked about his when his alumni association, he should have paid the lifelong fees day one because after 13 years he thinks he would have broken even. And this is ringing a bell for anybody. You were there that day? That was like the one day you were there, right? Yeah. So we're going to write an application that proves that he's wrong. So it's going to be a education in investing as well as objects and stuff like that.
So the person who does code gets to send it directly to him, and you can literally show them. It's like, see, ha.
That's fine. All of our code should show the same number.
Yeah.
All right. It's always funny when they think they can sneak in and I don't see them. So, we up here? Are we recording? Yo, you really suck at replying on Slack, by the way. Just terrible. Days ago, I messaged you. My last one actually told you suck at replying on Slack. You're no good to me if you're not checking that at least twice a day.
Okay.
By twice a day, it should be, how many of you would be okay when you ask me a question on Slack if I checked it like once a week-ish? That would kind of suck. Right? When usually I respond within like an hour, max. Sometimes it's like midnight and I'm responding like instantaneously.
Yeah, it's amazing.
And sometimes I do miss it, but very rarely does that happen. Okay, so we're going to look at arrays versus array lists. And this is kind of actually a topic that we're going to talk about in the second 8 weeks as well as most of next semester when we talk about data structures. So I'm not going to go too far into array lists in terms of how they're implemented. It's kind of unimportant for us, but I'm going to kind of make a comment here that array lists are kind of like something called linked lists, which we're going to talk about near the end of this course and most of next semester, this idea of linear linked data structures. So leave it at that for right now, just as a little hook in the future. But in general, what we're going to do is we're going to say which one to use. Did the book go into any details about when you might use array lists? What are they good for? Or maybe we should say, what are arrays good for? Because we want to compare these two guys. I saw a hand poking up somewhere. Go ahead.
Well, talking about array lists, it's more of like kind of like making sure the list is organized when in Java specifically.
Okay, what makes an array list more organized than an array? Go ahead. And don't try to answer the last question because there isn't an answer.
Store.
there isn't a good one for that. Go ahead.
Can it store a value other than its? Can it store like two separate can it store like a value inside of? Like if you had a strength, like you just like if you had like a.
Can it store more than one kind of value?
Yes.
Let's say yes, sort of, because this is the object. It can store objects.
Yeah.
And because of that, you technically could store a collection of things that are objects, and anything that we create could be an object. We can have fractions, cats, dogs, randoms. At some point in there, it's going to stop making sense in terms of a viable tool. That's kind of like buying this Tupperware container, marking it as shoes, and just using it as the junk drawer. Just throwing whatever in there where you kind of fish through it. Everybody has, all computer science folks should have that box of cables and stuff, right? Where like I can't find my USB stick or whatever it is. You go and look in the box. You gotta fish through this thing. And cables are the worst. Never put those on top. Plus they're even worse because everything, the small stuff shifts down through it. That's terrible. Bad news. So while that is true,
Yeah.
you could actually say the same thing about arrays. You can create an array of object types and put anything you want in there. All right, so probably not really a difference between them there. Anything else? We'll give one more try, and then I'll just give you the answer. This had to be in the reading. Nothing? All right, so just real quick, give me an example of how we build an array. So if I could say int array AR is equal to a new int array size 10, something like that. What's this guy imply? What's this creating for me? Okay. A collection. What's an array? If you had to give me a definition of an array, what would you say? We talked about arrays in, we talked about them in list form in the last class. Have we talked about the underlying stuff of arrays in here? All right, doesn't look like I have my picture for arrays. We probably talked about them last semester when we talked about contiguous memory. Remember that word? So this guy creates a base address. We know that an address is involved because of the new keyword here, right? New keyword creates addresses. Makes sense? So this guy creates a base address and reserves enough memory in a row. This is contiguous memory to hold 10 integers. Okay, where an int is 4 bytes, so this would give me 40 bytes of contiguous memory. That makes sense? That's what that line does. So it's going to create something if I draw a little picture here. How'd it go?
I have it today.
Oh. You got my reply last night?
Yep.
Okay. Yeah, those are all, I think, good. And you're job shadowing today?
Yep.
Let me know after that how it goes, and then we can put together a strategy for getting an internship.
Okay. Thank you.
Because you're not working directly with Mike today, right? Just
No.
You're shadowing somebody. All right. By the way, that's exactly how you should be using the Tech Talks. He scheduled a job shadowing with SkyGem, who was our first speaker. And I feel very confident that will turn into employment, paying him probably more than the Chancery does. But regardless, it'll pay him an experience, which will then pay him a lot more later on. Just FYI. Okay, so we have this variable AR. I'm actually going to steal this just to give you the picture from last semester. I usually when I originally teach this, I use less buckets than this, but we'll just go with it. Oh, and of course the indexes are green. This is bucket 0, bucket 1, bucket 2, bucket 3, 4, 5, 6, 7, 8, 9. So the length of this array is 10. Legal buckets are 0 through 9, so it's indexed just like strings are indexed. Okay, but now I'm going to throw something else up here. And these are, of course, in red. And just to keep my numbers simple, I'm going to say this is base ad. Well, I don't want to use that. I'm going to say this is base address 16 for no good reason other than I wanted a 2-digit number. So I just pretended like I got base address 16, 17, 18, 19. So this is 20, 24, 28, 32, 36, 40, 44, 48, 52. All right, so what happened in my example here is, and let me just grab this guy right here. We'll just throw this above. This is what gets created from that line. All right, the new keyword went and got us a memory address. So the value of AR is actually 16 in this case, which is the base address of this array. And what it did is it requested enough memory in a row, enough contiguous memory to hold this many, 10, of these guys, ints. And an int is 32 bits or 4 bytes. 32 divided by 8 is 4. There's 8 bits in a byte. All right, so an int is size 4 bytes. So if the new keyword happened to come back to AR and say, I found you a nice plot of land that can hold 10 integers. I went ahead and reserved that area for you, reserved all that land for you, and you can find the beginning of the land at memory address 16. Make sense? That's what's ultimately happening there. So AR holds a single value, the memory address of the beginning of the array, which is 16 in this case. Go ahead.
Quick question, are the memory addresses, do they go up by sequential order, or is it just that random? Well,
memory addresses would be in sequential order in that we talk about like the computer memory is just like one big long street.
Right.
You know, we talked about memory addresses, and anytime the new keyword returns something, it gives you this crazy looking memory address, and people get intimidated by pointers. But it's actually a far simpler addressing scheme than we use in real life. Real life, we have a house number, we have a street name, we have a city name, we have a state name, we have a country, you know, we have all these things that add up to where is this house in the world, right? Our system memory says this is house 1, this is house 2, this is house 3, this is house 4, so on and so forth. Every single thing in your computer lives in one big long street. We don't have to tell it the name of the street. We don't have to tell it the name of the town, the name of the state, any of that stuff. It's house number. That's it. And if you live near the end of the end of the street, it's going to take you a little bit to get there. is what's going to happen. All right. So that's how our computer memory works, which in principle seems very easy, but we represent it in hexadecimal values because those big numbers can benefit from having smaller footprints, which we get by representing it in hexadecimal. Make sense? All right, so, yeah, in any case. So the new keyword is going out and doing a task for us. What is it doing? It is giving us the memory address that is the very beginning of the memory that it has reserved for us. Now, as programmers, 99% of the time, we don't really care what that address is. If you get into C and C++ programming, there might be some situations where you do actually care what that address is because you might do some things called pointer math where you might mess with addresses. And that can be kind of interesting and stuff like that, but we're kind of seeing it here anyways. But generally speaking, the new keyword is a nice power tool for us, and we're just sending that minion out and saying, give me some memory big enough to hold a 10 bucket int array. Do your job. That's what we're saying. Okay? And it's coming back, and in my little example here, I said it gave me a 16. That's a memory address. So this would show up as like a, X16, a bunch of zeros and crap within there, whatever. Crazy memory address looking thing. Okay? Now, I've told you that an int is 4 bytes big. So 16, 17, 18, 19 is where the first int lives. 20, 21, 22, 23 is where the next int lives. 24, 25, 26, 27 is where the next int lives, so on and so forth. So this is a 4 byte bucket, a 4 byte bucket, a 4 byte bucket, so on and so forth. All right. So now if we wanted to print out a certain bucket of this array, we would say AR at bucket 0. What this is actually equal to is AR plus 0 times size of int. And so this actually equals 16 plus 0 times 4, which is actually equal to 16. Size of an int is 4 bytes. So if I want to go to bucket 0 of my array, I go to the base address of my array, 16. I add to it an offset. What offset? The number of steps I want to take times the size of those steps. How big of a step do I need to take? So bucket 0 would be there. If I said I wanted bucket 6, this would be AR plus 6 times size event, which would be 6 times 4, which is going to give me bucket 40. 16 plus 24 gives me 40, which happens to be where bucket 6 is. See how arrays work? Go ahead.
So you told it to do an integer size buckets.
Yep.
Could you store something like a char or some smaller in that bucket?
Absolutely. Well, you're saying, could I put a char in here? Mm-hmm. I could, but the char is only 16 bits. So the first 16 bits of that number would be unused. So I would be inefficiently using the space. Right? So giant Tupperware container, throwing a keychain in there. It's fine, fits. Wasted space. When you get into the OS class, you'll talk about different ways of, this would be considered internal fragmentation. So we have we have wasted memory inside. Who cares? We have lots of RAM. That's fine. But if you were going to store a bunch of chars, you probably wouldn't create an int array. You would create a char array. All right. So in this case, we're just deciding we want to store integers because that's the baseline, right? For any of these things here, arrays, array lists, whatever, these are collections of things. I want to store a collection of stuff under a single variable name. That's why we use these tools. Okay? So, AR at bucket 0, notice these math formulas are identical, right? What we're seeing here is the reason why arrays require contiguous memory. Because you can calculate using this syntax. We allow ourselves to have this convenient syntax. Give me bucket 0. Give me bucket 6. And what it does is it uses an identical math formula under the hood to always start off at the base address and then take some number of int size steps to get me to where I want to go. And we can just calculate that position. So start at base address, whatever AR holds. In this case, it's 16. Add to it 24. We end up at memory address 40, which happens to be where bucket 6 lives, right here. Make sense? All right, so that's how arrays function under the hood. Now again, from a programmer's perspective, now from a computer scientist's perspective, you should understand this because this is valuable information that I know might not seem that beneficial, let's say even say most of the time. At some point, especially when you're working with some older languages or you're solving some more complex problems than maybe we solve in class, knowledge of how this is represented under the hood might allow you to solve a more complex problem. All right, so from a computer scientist perspective, this is important. From a everyday programmer's perspective, we don't necessarily need to know this level of detail in order to use an array. You don't need to know how a combustion engine works in order to drive your car. Something goes wrong, or you're trying to do some sort of mod on your car or something like that. You're a car person, the computer scientist of cars, right? It might be helpful that you know a little bit about what's going on when you start unplugging things and unscrewing things and stuff like that. Okay? So what we're looking at here is the computer science level of this, which I'm telling you is important, but it's only important for that last percentage of the time. Something I talk to parents about quite often, because usually I'm dealing with, this would have been most of you a couple of years ago, right? The students don't really know what they want to do, but mom or dad wants to know every little detail about the program and every little thing about everything. Is what differentiates higher education from like the coding boot camps, right? Because we're in competition with a bunch of other things out there. So you can skip the whole, if you want to be a computer programmer, you could skip the whole college degree thing, right? You can go down, there's like I forgot what it's called down in Milwaukee, but there's one in Milwaukee, there's like 10 in Chicago where, you give them a bunch of money, some of them even it's free. And then they take a percentage of your first 3 years of paycheck. So they train you, it's like a 6-month very intensive programming course, right? They train you on how to program. Usually it's like a technology like Ruby on Rails or something like that, which is quicker to learn but hides a lot of stuff from you. Then they guarantee you a job, and then they might take 20% of your salary for the first 3 years. So you go out and get a job for $50,000 a year, let's say, and they're taking 10. So they pay themselves, they're taking, 10. So then they pay themselves $30,000 for teaching you for 6 months, something like that. But only if you get a job. It's a pretty good deal, right? So a parent might ask, well, why shouldn't I just do that? Cost me $0 and my kid goes and gets a job. Well, you can, and you're going to get a job. And with that skill set, you'll be able to solve 60% of the problems. So you're going to be a programmer in this. This isn't any different than maybe you go to one of those quick lube oil change places, and there's 5 people that work there, and probably 4 of them know very little about cars. They know exactly how to change oil, right? You might have the one person there who knows quite a bit about cars, maybe the manager or something, but they're the mechanic person out of everybody. But those 4 people who only know how to change oil, they went through the coding boot camp. Right? They can change your oil really, really well. They can do a couple other things, fill the tires, change your windshield wiper fluid, whatever. There's a set of stuff they know how to do well. But the second you start getting out of what they've been trained on, they can no longer solve problems. They don't have a theory to fall back on. That's where your undergraduate degree comes from. So now you can solve the next 20% of those problems because you have an underlying theory of computer science. So now you're up to solving 80% of the problems. What does the master's degree get you? It gets you maybe the next 10% of the problems. Okay, because now you have even a deeper understanding of the theory of what you're working with. So now somebody with a master's degree has 90% of that knowledge from it going out in the workforce doing stuff. PhD probably doesn't get you any more problem-solving ability because it becomes very, very theoretical, not really applied. So where does that last 10% come from? Talent and experience. Yep. That's it. So we just built the whole career model into why you should get a master's degree if you want to get to a higher level within the doer community, let's say. And if you want to teach, go and get a PhD. Otherwise, don't waste your time on a PhD if you just want to work. Okay?
Do you think like a lot of people that go to the coding boot camps will kind of fall out, like the guy from Tesh was saying?
100%.
Yeah.
What they'll do is they'll get into a job and they'll be good at it. They'll be good at doing the oil changes. And as long as they're willing to do that the rest of their life, they'll be fine. But they're going to hit a ceiling for what they can earn, right? And they, outside of talent and external practice breaking them through that what they didn't learn in an undergraduate degree, which can happen, right? You have outliers. Outside of that, they're going to be in a thing where they're going to get their 2 or 3% raise per year as long as the company's doing well and just keeping up with inflation, making a reasonable living. I mean, $50,000 a year is not You know, you're not starving. You're fine at 50,000 a year. Many of you would 50,000 a year. I'd make $8 an hour at the Chancery. I've been skimming other people's tips. That's how desperate I am. But from a computer science world perspective, 50,000 a year is nothing, right? That's chump change in your career path here. There's no reason why after you've been working for, the Acuity folks that are coming in to speak to you today, they probably won't advertise their salary to you, but both, I only know the two that are coming in, Josh Curcio and Brendan Lindsay, both came out of here, and they're both making 70 something. And they've been in, they've worked at Acuity for 3 years now. 2 years? I think this is their third year. They're starting their third year.
70?
They started at 65. That class. This year's class, so I think they're making like maybe upper 70s, 77 or something like that, because they just, after 2 years, you move up to the next level there, and that's like a pay raise with that. So they came in at, let's say, 15,000 higher than you'll come in at from a boot camp, and they are, after 2 years, making let's just say 25,000 more than you would come in at the boot camp, and the boot camp probably is going to have you hit a ceiling of 60 plus cost of living inflation based things. So they're already past where you'll ever get to with the boot camp education, which doesn't mean it's bad. You're just prepared for a different career path. So it's not a direct competitor is the punchline. So when you consider the cost of an undergraduate education, let's just throw a number on it, 100 grand, something like that. Is that a pretty simple round number? Mine, whatever. Even if you were paying that out of pocket, that's 4 years of working at Acuity, and now you're net positive. That's pretty good. All right, so in any case, that's why you should not only get your bachelor's, get your master's, and don't get a PhD unless you're going to teach, or you're going to go do research at like Lockheed Martin or something like that. That might require a PhD. Google also typically hires PhDs because they want people working on some of their weird projects. But generally speaking, you're going to max out your earning potential as a coder in the workforce with a master's degree. Anything beyond that, you might even have to not put on your resume. Because places that are not Google might look at it and say, we're not even going to interview this person because we probably can't afford them. The perception will be they'll have to pay too much for a PhD. They're willing to pay for the master's degree because the master's degree might be kind of like a bachelor's degree with 3 years of experience. It's probably viewed as very similar, but you can do a master's in 3 semesters. Here you can do your master's. We just got our new scholars program, so you can actually do a master's and bachelor's in 4 years. And if you're not in the scholars program, you can do a master's and bachelor's in 5 years. So we cut a semester off. So you trade 1 year for 2 years you're still ahead money-wise. So actually, higher education makes a lot of financial sense, but yeah, it is what it is. All right, so that's why understanding this kind of stuff actually does have value. You just might not necessarily be able to see that value instantaneously. Just like when you drive your car on an everyday basis, you don't necessarily need to know what's happening under the hood. But every now and then that might come in handy. Okay? So we use these guys as for collections of things. So what's good about arrays? We're going to say pros. Really fast. We can calculate basically instantaneously. This is a very static math problem. This is not you doing hard math, right? We're not doing integrals and derivatives and sines and cosines and crazy stuff. This is just adding and multiplying. Okay, so simple math that gets us a memory address, and the way our computer is built, we can just go to that memory address. We don't have to walk the street. We have the high-speed train that takes us from point A to point B really, really, really fast. So if I know I need to get to bucket 40, to memory address 40, I can effectively teleport to memory address 40 inside my computer. Fast. What's up?
No, it's just, it's like sound. It's like the Jew.
Oh. All right, so does that make sense? Navigating that street in memory, if you know exactly which house you're going to, you can just get there. Arrays are really fast. Cons. What's wrong with arrays?
It's very difficult to add memory.
Yeah, so it's these guys are really fast and they are memory inefficient. I have to know exactly how many elements I'm working with here. So I'm saying build me a bucket, get me a container from Target that can hold 10 integers. Now I could choose to put less than 10 things in there, and I could just say, I'm just being a little wasteful. I didn't fill the bucket to the brim. Okay? But if I need to hold 11 or 12 things, in real life, what might we do? We might kind of start piling up above the, okay? That's called a memory leak in computer speak. Okay, if we only have reserved 10 spots and we're using spot 11, 12, and 13, we might be using somebody else's reserved spot. Make sense? Somebody else might have called the new keyword, and the new keyword said, yeah, we're going to give you this area. Now, all of a sudden, if your neighbor's building on your land, you're not happy. Right? Okay. And in computers, things crash when you're not happy. Right? Make some sense? So arrays, super, super, super fast. These are the right tool for the job if you need to store a collection, either a known size of a collection or a reasonable maximum size of a collection. The first thing I said there is the absolute truth. If you definitely know that I need to store exactly 10 things, arrays are the right tool for the job. If you know you will never need to store more than 500 things, let's say. That's a small enough number. We say, well, we got plenty of memory in our computer. Who cares about reserving a 500, I guess it would be a 2,000 byte chunk of memory, right? I'll just say, that's mine. I'm not going to use that most of the time. In fact, I may never fill it. But that's the biggest it might ever get. I'll just go ahead and reserve that, and then I'll fill it as needed. Something like that. You might say that in a certain application where speed is imperative, then it might be worth being a little wasteful of memory at the cost of gaining that extra speed. Make some sense? All right, so now for array lists, so this is an array.
Okay.
This is an array. This is old school. This has been around since, well, before C, but let's just say that our style of arrays today, this syntax right here, is pretty similar to what you'd see in C. All right. The C version of this would look like, you could actually write something similar to this, but let's write the scary version of this in C. It would be int pointer AR is equal to malloc 10 times size of int. This is memory allocate.
Oh.
So that's the new keyword back then. Go ahead.
So that's how you would call the array in Java? The one underneath that?
Yeah, this is Java. This is Java, C#. It'll work in C++. Yeah. So all your modern languages like this, but it came from this. But this says the same thing. This says, I want to allocate some memory. How much memory? Whatever the size of an integer is, times 10. That'll go and get you a plot of land that is big enough to hold that many of those guys. All right, but then in C, you could say AR bucket 2 with the square brackets. Same syntax works. It's been around for a couple of days. All right, makes some sense?
Yeah.
All right, but you're not going to have to write this now. And by the time you start doing some C and C++ stuff, and you are writing this when we really get into pointers, this won't be as scary. Yeah, the point is right now, we're less directly working with memory because Java mostly hides it from us. Make sense? Not that we can't tell that it's there. Not that it's not happening under the hood. But Java doesn't really, it's kind of like those sealed motors. What is Honda? I think Honda makes a sealed motor. You can't get into it. So even if you're a mechanic, at least on boats, this is the way it works. If you're a mechanic on it, they have a sealed motor where you have to, it's kind of like the Apple version of motors. You got to take it to a Honda place that has the magical whatever to get inside the brains of the motor. All right. So Java hides the stuff from you. Not the end of the world, but as computer scientists, we know what's going on under the hood. So that's an array. Now, I'm not going to talk about how array lists actually work, because that's kind of when we start getting into linear linked data structures. I mentioned linked lists earlier. We start talking about how they actually work. So for right now, we're going to pretend like it's the magical engine, but let's talk about the, so an array list still holds a collection of stuff. The pros, we don't need to tell it how many things we will hold. So it's flexible in terms of size. Cons, well, we might say this guy is, well, we would also say memory efficient. And you'll just have to believe me for that now, since I'm not going to show you how it's implemented under the hood with this linear linked data structure. So it's also memory efficient because it's only going to grab a small chunk of memory. Array lists are kind of a hybrid between a linked list and a real array. So they're going to grab they're going to say, I'm going to go ahead and just get this much memory. And as you start getting towards the end, I'll go ahead and just grab a little bit more. And we'll kind of move you over magically. You don't have to worry about it, blah, blah, blah. But I'll take care of it is kind of the idea. But it will initially grab an amount of memory to give you some wiggle room. And then as you start filling it up, it will grab more memory and more memory so that you don't have to worry about adding an extra thing or removing something, whatever. Go ahead.
If the code is more flexible and stuff like that, what makes it, so why do we use arrays at all? If array lists have this. Oh, yep, there. Oh.
Slow.
I didn't see that.
I just wrote it while you were, I answered it in text. So I texted you. Yeah. Now, really the way I should write this is relatively slow. That is to say, our computers are really fast, we probably won't notice. So to your point, could you get away as a professional developer never using a traditional array and just always using an array list? The answer is probably. We could probably throw another one of those 98, 99% things on it. Other developers might look at you like you're weird or something, like, why aren't you using the right tool for the job? Well, I got 32 gigs of RAM. Okay? I don't care. And keep in mind, this is a very different conversation than we would be having if it was 1975. Because then, people, if array lists existed back then, they didn't. But if they did, linked lists did. But so I guess we sort of had them. But you would have a very different conversation with a coworker then. The coworker would say, why aren't you using an array here? You know you only need to store 10 things. And you would say, well, an array list gives me the flexibility. He says, well, that flexibility means that I can't run my program on this hardware because you're taking up all the RAM. Make sense? It was a very different world of hardware back then. Now, $20, you got another 16 gigs of RAM in your machine, move on with life. That's a lot of ints. It's 16 gigs of RAM. Go ahead.
If you sort an array in a useful manner, can you speed up the speed of it?
You mean an array list?
Yeah, an array list.
No, because the slowness of it has to do with how it's actually represented under the hood. So I'll just throw this out there. This is not stored in contiguous memory.
So it's like a linked list that you just kind of
Yeah.
code as an array.
Yeah, you have a node which links to another node someplace else in memory, which links to another node someplace else in memory. It grows as it needs to. Array lists, I mentioned, are kind of hybrids, where you kind of almost have an array which links to another array somewhere in memory. So it just kind of finds like medium-sized plots of land and kind of throws them all over the place. So you have some speediness in certain areas at the cost of a little bit of memory and efficiency. And your slowness is only realized when you have to jump to a different part of memory. That makes sense? So it's a hybrid-y type approach. But it's fair for us at this level just to say we're not guaranteed that the entire array is in contiguous memory. The entire array list is in contiguous memory, and therefore it could be relatively slow compared to an array. But what I'm telling you is unless you're doing something with really, 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 really big data on a really slow machine, you probably would not notice the difference, even though I'm telling you under the hood there is a difference. Okay, this guy is getting 1 mile per gallon. The other guy is getting 60 miles per gallon in the car. You probably wouldn't buy the 1 mile per gallon vehicle, right? But if you had unlimited gas for free, you might not care, as long as you had a big enough tank. Because you don't want to spend your life at the gas station. But if you have a, million gallon tank, and you only get 1 mile per gallon, that's 1 million miles you can go. Maybe you would never go to the gas station, unless you really do a lot of road trips, I guess. Go ahead.
So array and array lists are similar ways to store information, which have slight differences in how they store that information.
Absolutely. Yep. They both store stuff. How they store it under the hood is a little bit different. That has some consequences. But it would be fair to say, getting back to your original question about why wouldn't we just always use array lists? In today's world, you could probably make the argument that an array list is always going to be more convenient. Where always is a 99% type of answer. As computer scientists, we should try to use the right tool for the job, right? But if you think about, you're working around the house or something like that, you can screw anything in with a power drill. So,
How would we better use your array on like a video game or something where memory is important?
You would have to do more definition of what the game is. If we had like a 8-bit video game running on today's hardware, you could write it in the most inefficient way as possible. Mario will still move too fast. Yeah.
I was thinking more along the lines of like Destiny.
Yeah, a modern video game, that would be that 1%, where you are trying to push modern hardware as far as it can go. So any little place that you can be efficient, you want to be efficient. Yeah, absolutely. Arrays would make a lot more sense just looking at that angle of things in a situation like that, because you do have a fixed amount of memory, especially in consoles. Because, in our desktop computers, you can just throw more RAM in. In your console, you're kind of matching it used to be you were matching, all PlayStation 3s were the same, right? Now you have a couple of models of PS4. You have the Pro, which has more, Yeah, so that's load speed. So that doesn't necessarily change what you're developing for. But the memory and the processing speed, that does make a difference. Before, you were writing your game and you could optimize it for that. Yeah. As long as my game runs fine on that, everybody's happy. Now all of a sudden it's like, well, I have to write it for that, and then I can have the extra better textures on that. So you get some fragmentation. Okay. So both these guys store stuff. Arrays allow us to array lists. So let's just kind of maybe give a why array list. And I'll be honest, and I'll say I very rarely use array lists. Typically, if I'm either going to use a array or I'll use a linked list, which, from your perspective, the way you'll use it is almost identical. An array list. In fact, if we do Java array list, and look at the documentation for that guy. Here's ArrayList. So an ArrayList is an abstract list. Oh, interesting. So list isn't even, so if I say Java linked list, see that there's a linked list is a sequential list, which is an abstract list. So they're doing more stuff in this. So a linked list has a lot of lineage in common with an array list. Just instead, array list ended right here, where we've inserted, instead of array list, an abstract sequential list, whatever that is. It's a list in order of abstract types. And then we have this thing called a linked list that's after that. Talks about the different ways you can accomplish collections of stuff. I almost always use linked lists for no other reason than the time period I grew up in, we wrote data structures, and I learned about linear linked data structures, which array lists are a hybrid of. Linked lists are built into Java. I've used linked lists for 35 years. That's what I pick. Works, but I solve the exact same problem that you would solve with an array list, and I don't really worry what's happening under the hood. The second I use a linked list, I'm immediately agreeing to have a lower performance situation that probably would not be noticed. Okay, so we go back to this Y array lists. These guys are very flexible in terms of what they can store. Let's say what and how many things they can store. And then we'll just say they are fast enough for most applications. And that's where your argument for you can pretty much always use array lists and get away with it. Even though I'm telling you I will rarely use array lists. But I often use linked lists, which you could just use as a synonym for array lists. All right. Now we have this thing called generics. And let me show you what I mean by this. So I'm going to go into Eclipse here. We'll just gut this for a second. Now, if I go ahead and say I want an array list AR is equal to a new array list, it's going to want me to import, was it java.util? Java.util array list. So that's where array lists live in the library java.util. So we have some utility stuff. You want to store flexible data sets. Here's your array list. All right. Now I'm going to say ar.add. Now, I don't know if can you see that on the screen there, that this guy takes in an object. Make sense? So a default array list, if I don't build it anything special, let me just remind you of something here real quick. Remember when we first started talking about objects? At the very top level here, we have the object data type. And then more recently, we built, for instance, a fraction. So we built a fraction, and a fraction is everything that an object is, but then a little bit more. Has numerator, denominator, knows how to add itself to other fractions, things like that. Okay? So in the object hierarchy in an object-oriented language, this is not just a Java thing, this goes to any object-oriented language, this top-level object is always an object. So when I say I want a plain Jane generic array list, I can add a new fraction 1/2 to that guy. All right, and that's perfectly legal. All right, so now if I say system.out.print, actually fractions have a display method. So I'm going to say ar.get. I'm going to give it an index. And notice what it returns here is an object, a generic object. So I'm going to say get from index 0. Dot display. Now notice it's yelling at me and saying that display method is not defined for the type object. Doesn't know about a display method for objects. So I can say, well, I happen to know that this guy is actually a fraction. So AR.getBucket0 is going to boil down to a pointer, a memory address that will point to an object somewhere. I happen to know that that object is a little bit more than meets the eye. It's actually a fraction. But because of the way I built my array list, it comes out as a generic object, pointers to other pointers. So if I want to use it as a fraction, I need to remind Java, look, I've identified this guy as a fraction because I know that's what I put in there. Therefore, I'm going to typecast it to fraction, have all these parentheses and stuff. So everything I've highlighted there is an instance of the fraction class in which I can call my display method on that guy. So that gives me my fraction 1/2. Make sense? But because I built this array list generically, I didn't get the ability to conveniently use my array list. So I'm going to go ahead and comment this out here for a second. So I'm going to use generics. I'm going to build an array list in terms of fraction objects. And this is going to be a new array list of fraction objects. Now, I'll just go ahead and type it here. When I say ar.add, notice the kind of value it thinks that I'm going to be passing it. It's now expecting me to pass it a fraction. This guy has now been notified that you are not a plain Jane array list. You are an array list capable of holding fractions, and as such, we've updated all of your special functions so that they will take in fractions and they will spit out fractions so that when you use this array list, you don't have to do any special typecasting. You can just use it. So now I can say ar.get from bucket 0 dot display. This guy will spit out a fraction because I have built my array list in terms of fractions. That makes sense? It's still an array list. It's still a collection of stuff. But when I built it, I used the special syntax for generics here. And that special syntax allows me to specify that this guy right here is a special kind of array list where I want all of his functions to be flagged with the fraction type. So I don't have to do typecasting every place, all over the place. Because the majority of the time, when we are creating collections of things, we're creating collections of very specific things. Very rarely are we going to want to have that junk drawer array list that can hold anything that is an object. Just because we can doesn't mean that that would be all that helpful in problem solving. That makes sense? All right, so this is that generics syntax. In fact, I'll just copy that in here. Came in very funny, but let's just call that good enough. All right. Because that really kind of tells the story, right? I mean, sometimes, what is a picture is worth 1,000 words? Code is worth 10,000 words. Assuming you can read code. Yeah.
So if we give it the generic for fractions, will that give us any problems if we like toss in like a string?
Yeah. It'll give you major problems. Yeah, so I've told this guy, you're built for holding fractions. So now if I say ar.add, and I give this guy, hello, I'm a fraction, something like that, okay, he's not going to be overly happy here because I've thrown a string in there. Make some sense?
Yeah.
All right, so we have the Acuity folks here. By the way, that's Josh Curcio. I'm going to stop the recording here. I'm going to put up another reading assignment for Thursday. It'll be an impossible one. I'm going to do 9 chapters.
Still, thank you. I have so much fun.
But we will have a homework assignment over the weekend now that we've covered through this array list stuff. All right. So before I turn it over there, questions, comments, concerns, bribes?
Okay.
All right. Don't go anywhere. The Acuity guys are